Hi friends, in this video we are going to discuss about part of DC machine. Right, in this video the first one, yoke. Yoke made up of, can you tell me? Yoke made up of cast steel or cast iron. This is made up of cast steel or cast iron. Generally, for high rating applications, we are using cast steel. For low rating applications, we are using cast iron. Generally, this yoke provides outer protection layer. What is that? It provides the protection from outer side. That's why it is called a outer protection layer is our yoke. And it provides mechanical balance to the machine. What it provides, sir? It provides a mechanical balance. This is also important for our machine, not for our examination actually. So, made up of cast steel or cast iron, outer protection layer, it provides mechanical balance. And generally, the main function of yoke is it provides a low reluctance path for flux. Low reluctance path for flux. This is the main purpose of our yoke. Actually, you saw already, actually our machine is like this. Yes or no? Like this. When this is connected to like this and is like this, here the flux is coming like this. In this 50% of flux is come like this and remaining 50% of flux is like this. Nothing but it provides a low reluctance path for the flux or return path for the flux, and the yoke carries only 50% of total flux, not the 100%, because in this 50% flows like this and 50% flows like this. So it carries only 50% of the flux only. This is generally the purpose of yoke and the yoke points. This is in generally very common thing. They may ask you in competitive exams. And second one, pole core. This pole core also made up of cast steel and cast iron. Is the same. Sir, what is the purpose of pole core? The pole core provides accommodation for field winding. This is the main thing here in pole core. It provides the accommodation because generally pole core is like this. We are placing winding on pole core. Actually, the yoke and pole cores are no need to laminate. In generally, no need to laminate this pole core as well as yoke, but in modern machines, this pole core and yokes also laminated in order to get the maximum efficiency or minimum losses. It is possible, but not required. If it is done, we can get somewhat increased efficiency. This is about generally the pole core. And next one, the third one, the much more important than these two, is the pole shoe, which is very important in our DC machine. How it is the pole shoe? Let's see here. Actually, we drawn in our construction diagram, the pole shoe is like this. This plays a major role in our DC machine. Generally, this is pole core where we are placing the field winding, and this is pole shoe. For example, this is my armature core. The two pole shoes are like this. This pole, for example, north pole, and this is south pole. This pole shoe provides uniform air gap to the armature and uniform flux distribution to the armature. This is the most important point. The purpose of pole shoe is which provides uniform flux distribution to my armature. Getting or not? Generally, the distance between two poles is called pole pitch. Pole pitch is nothing but the distance between two adjacent poles. For example, this is my pole pitch. The distance, this is pole pitch. In this, actually, some part is covered by this pole shoe. And here, that part, see here, actually, this is called pole arc. What it is called? Pole arc. The percentage of pole arc in our pole shoe, how much percentage it will cover in my pole pitch? If they ask you a question, the pole arc occupies nearly 70 to 90% of pole pitch. This is also important thing here. Nothing but the conductors under the pole arc is 70 to 90% of pole pitch. Like that, they may ask you question. Already gate question is there based on that. Be careful. So this is important. Pole arc occupies around 70 to 90% of pole pitch. Our pole arc is equals to 0.7 to 0.9 times of pole pitch. This is simply question. And generally, the pole core and pole shoes are attached by countersunk screws. What is that? Here, the pole core and pole shoes both are riveted together, attached by countersunk screws. This is also, you have to remember the point. Okay, this is simply about pole shoe. If they will ask you a question, option A, yoke, option B, pole core, option C, pole shoe, option D, all of the above. Which of the following is very important to laminate, very required to laminate? Tell me which one. Here, the pole shoe is we have to laminate. So, the pole shoe made up of silicon steel laminations. This is an important thing. The pole shoe must and should laminated in order to reduce the eddy current losses and to increase the efficiency, because here more flux is there. Among these three, the must and should required laminations for pole shoe only. Getting or not? Are you getting my point? Right, sir. So up to now, this is about pole shoe actually. So here, listen carefully. In generally, we have seen two types of poles. One is this type of pole and other one is this type of pole. These are called arc poles or broad poles. These are called eccentric poles, or these are also called tapered or chamfered poles. Chamfering poles, right? Chamfered poles are eccentric poles, and these are called broad poles or arc poles. Generally, these are used in DC machines and these are used in synchronous machine. And this provides the more average EMF is nothing but trapezoidal EMF. and this provides the more maximum EMF, nothing but sinusoidal EMF. To get the sinusoidal EMF, we should have eccentric poles. If you have more average, nothing but a trapezoidal, likewise we have to use arc poles. Are you getting or not? Next one, generally the poles are two types. One is the all poles are same, for example like this: north pole, north pole, north pole, north pole, or south pole, south pole, south pole, south pole, like this. And another way of poles are, up to now we saw north pole, south pole, north pole, south pole, like this. These are called what it is called? Homopolar poles, or homopolarity simply. These are called heteropoles. Heteropolar. Homopolar system, heteropolar system. Generally, this heteropolar system used in AC machines and DC machines. If you are using in AC machine, the EMF induced is AC. If you are using in DC machine, the EMF induced is AC. Whatever the machine, the EMF induced in the system is AC. But we required DC, right? By using commutator, by placing the commutator, we can convert that AC into the DC. But this homopolar system only used for DC machines. And here it produces the EMF of DC. No need of commutator. This is very, very, very important. Homopolar system is only used in DC machines, and here no need of commutator because the induced EMF is DC. But the heteropolar system used in AC and DC machines, here the induced EMF is AC. By using commutator, we can get the DC output in DC generators. This is simply about heteropolar system. Sir, why we are not preferring this one? Now, in generally, where we are draw heteropolar systems only, why we are not preferring homopolar in DC machine? Because costly and manufacturing difficulty. Costly and manufacturing difficulty and less EMF. That's why we are not preferring this one. Always we are preferring heteropolar system for DC machines and synchronous machines. Is it okay? Fine. Right, sir. This is about generally the pole shoe, which is very, very, very important up to now. Are you okay? Are you getting or not? The pole shoe is the third part, very important one. Next, the fourth part, I said you already, armature core. Now tell me, what is the armature core? Generally, in DC machine, for commutation process, armature placed on rotor only. Armature is a rotating part. The armature core made up of CRNGO, silicon steel laminations. This is what actually. Here again, the laminations are made to reduce eddy current losses. Silicon steel used to reduce hysteresis losses. In that, silicon content is 4 to 5% only. No need of grain orientation, just cold rolled is enough. This is simply the armature core made up of. Are you okay? Of course, the armature core is made by laminations. Pole shoe and armature core must require the laminations. You should remember this point. Okay, sir. Next one. Generally, the armature core having slots in which we are placing the armature winding. That armature winding, which type of winding we are using here? In our DC machine armature, this is a rotating, that's why we are using distributed winding. Rotating machines mostly we are using distributed winding, and this is DC machine, that's why we are using full pitch winding. So in DC machine armature we are using full pitch distributed winding only. Are you clear? Right, sir. Now, this armature core having different types of slots. In generally, for different machines, we have different of slots. The slots are three types. One is the open type of slots, and other one is the semi-open type of slots, and next one is the closed type of slots. What is that? Open type of slot, semi-open or semi-closed type of slots, and closed type of slots. In generally, here air gap length is more, here air gap length is medium, here air gap length is less. Here easy winding procedure, here difficult, here very difficult winding procedure. Very difficult to winding. In generally, when air gap length is more, the power factor is less. When the air gap length is less, power factor is more. Here, medium power factor is maintaining. Now tell me, which is preferable for DC machines? In DC machine, no worry about power factor, it is always unity. So, easy winding and less costly is better. So that's why in DC machine we are using open type of slots. What about in induction machine? In induction machine power factor is very important. That's why we should use closed type of slots, but this is very difficult and costly and time taken. That's why finally we are using semi-open type of slots in our induction machine. But in small induction machine, in laboratory applications, we are using closed type of slots, of course. And then where we are using closed type of slots? Only in laboratory applications. Next one, for synchronous machine, which type of slots we are preferring? Synchronous machine, actually power factor is important, that's why we should use this one, but this is costly, difficult to winding, that's why we should use semi-open type of slots, but we are using open type of slots. Why? Why, sir? Because in synchronous machine, stability is more important than power factor. The stability directly proportional to air gap. That's why we are using synchronous machine open type of slots. Sir, what about power factor, sir? Power factor can be varied by excitation. This is the special offer for the synchronous machine. We can change the power factor by changing the excitation. This is the additional advantage of synchronous machine. So whatever, in DC machine we are using open type of slots, in synchronous machine we are using open type of slots, in induction machine we are using semi-open type of slots, but in small induction machine we are using closed type of slots. This is simply about the armature core. Are you okay? Right? It is clear about armature core. And next one, what is next one actually here? Let's see the fifth one and sixth one. Fifth one is the armature winding, and sixth one is the field winding. Okay, let's see about these two. You know already, yes or no? See, the armature winding placed in armature core, the field winding placed in pole core. This is a rotating winding. This is a stationary winding. Rotating, that's why this is distributed winding. Stationary, that's why this is concentrated winding. Which is stationary, concentrated, which is rotating, distributed. Is it okay? Right. Here, generally, the armature winding produces EMF, the field winding produces magnetic field. You know about this. The armature winding produces AC EMF, the field winding excited by DC supply. This is excited by DC supply, this produces the AC EMF. And generally, this having the armature resistance RA, this having the field resistance RF, in generally, the armature resistance is very less, the field resistance is more. This is in the range of 0 to 1 ohm in between. But this is in the range of 100 ohms. So always the armature resistance is less than the field resistance. This is also important. And the armature resistance is the example for low resistance. And field resistance is the example for medium resistance. Medium resistance example is field resistance. Low resistance example is armature resistance. Yes, up to now clear armature resistance and field resistance. This is simply the difference between armature winding and field winding. And here this field resistances are again two types. Our field windings are again two types. Let's discuss about that field windings here. Here armature winding is completed. Now let's discuss about field winding. This is important. The field windings are two types. One is called series field winding and other one is called shunt field winding. The series field winding which is in series to the armature winding. What is that? This winding which is in series to the armature winding. Shunt winding is nothing but this is in parallel to the armature winding. This is the what is a series field winding, what is shunt field winding. Generally, this resistance is called RSE and this resistance is called RSH. This is series to the armature, that's why this value is less. Of course, this value is more. The shunt field winding resistance is more. So finally, the armature resistance is less. Of course, the series field winding resistance and armature resistances are mostly same. And these two are less than shunt field resistance. Of course, the compensating winding resistance also same. These three are very small values, but RSH is very greater than these three. This is simply the different resistances in our DC machine. So RSH is more and this value is less, RSE is less. Okay, so apart from this, generally the series field winding having less flux and shunt field winding having strong magnetic flux. This is comparatively weak magnetic flux. This is comparatively strong magnetic flux. Actually, if you remove this, if resistance is less nothing but R is equals to rho L by A, if resistance is less nothing but more area, here area is more, if resistance is more nothing but rho L upon A, less area. If flux is less nothing but flux phi is equals to mmf upon s is nothing but ni upon s. If flux less nothing but less number of turns, flux more nothing but more number of turns. Here, the winding having more cross-sectional area, less cross-sectional area. More cross-sectional area nothing but thick conductor, less cross-section area nothing but thin conductors. Here, less number of turns, here more number of turns. Now tell me, the series field winding nothing but less number of thick conductors. This is the series field winding, less number of thick conductors, less number of thick conductors. What about shunt field winding? Shunt field winding is a more number of thin conductors. This is the shunt field winding, and this is the series field winding. The differences between shunt field winding and series field winding. This is very, very, very important for competitive examination. Are you getting or not? And next one, here, generally the armature winding and field windings are two different windings. We know that armature resistance and field resistance are different, right? Here, the number of field coils is equals to number of field coils are nothing but number of poles. This is one thing. But number of armature coils nothing but number of commutator segments. This is also very, very, very important. Number of commutator segments is exactly equals to number of armature coil. Number of poles is equals to number of field coils. If number of armature coils are more, then we can get a pure DC output, because more number of commutator segments, the commutators which gives the DC, that's why more number of armature coils gives us pure DC output. This is a very, very important thing here. Are you clear? Okay, so this is about the armature winding and field winding and its differences. Is it clear? So up to now we completed yoke, pole core, pole shoe, armature core, armature winding and field winding. Now we have only two, that brushes and commutators. Okay, let's see. So in this video, brushes and commutator segments. So generally, brushes made up of carbon, graphite or copper. On a difficult manner, copper also used. Generally, why the carbon and graphites are more preferable? Because the carbon and graphites having self-lubricant property. That's why this carbon and graphites are more preferable than the copper. Is it okay? Right? Next one. And also, carbon and graphites are highly resistive. When high resistance is there, we can have a good commutation. This is also another reason to get the carbon and graphite brushes more than copper. In this, generally, electrographite or metal graphite or carbon graphite. Generally, these are used for high rating applications in generally. This is also very important. And generally, the carbon and copper copper is used for low voltage, high current applications, and carbon is used for low current, high voltage because this is high resistive. That's why low current. Normally, this is low voltage and high current. These are the generally about brushes. Here, what is the purpose of brushes? Which collects the current. What is that? This is which collects the current actually. This is the purpose of the brushes. And in generally, the brushes are placed along the always brushes placed along MNA, not GNA, not Q axis. MNA is 100% correct answer. Sir, why sir? Generally the commutation takes place along the brushes, nothing but which collects the current. During the current collection, the EMF should be less. If EMF is less, then sparkings also less. If sparkings are less, that is a good commutation. To get the good commutation, EMF should be less. At MNA, not less. EMF is equals to 0. That's why the always brushes should be placed along the MNA for good commutation. I said you already, MNA axis is also called brush axis. So here, which collects the current, these are always placed along the MNA because at MNA EMF is 0, so less sparks and good commutation. And what is next? Generally, the brushes are gives the drop, right? So total brush drop is equals to total brush drop is equals to 2 times of each brush drop. The total drop due to brushes actually. The total drop due to brushes is equals to 2 times of each brush drop. This is the total drop due to brush. In generally, we are taking the brush drop is 2 volts. How much it is? In generally, we are taking the 2 volts as a brush drop, but the total drop due to brushes is equals to 2 times of each brush drop. And the brush current is equals to 2 times the each parallel path current. This is also brush current is equals to how much, sir? 2 times of the each parallel path current. And generally brushes, the adjacent brushes are opposite polarity always. If this is positive, adjacent should be negative, like that. The brushes are adjacents are opposite polarity. This is simply about the brushes. Sir, how many brushes we are using? This is based on winding. If it is lap winding, number of brushes is equals to number of poles. If it is wave winding, number of brushes is equals to 2. Number of brushes is equals to number of poles. That is equals to number of parallel paths for lap winding. Number of brushes is equals to number of parallel paths is equals to 2 for wave winding. You should remember this is also. I will tell you again in lap winding and wave winding. So up to now about brushes. Okay. Next one, commutator. Commutator or split ring, both are mostly same. Actually, split ring plus brushes combinedly is called commutator. This commutator or split ring made up of hard drawn copper. Made up of what is that? Either phosphorus branch, silicon branch, or hard drawn copper. This is more preferable. Number of commutator segments is equals to, I said you already, number of armature coils. Generally, the commutator nothing but a rotating, what is this? This is a rotating, uncontrolled uncontrolled full wave rectifier or inverter. Both rectifier or inverter. Commutator is nothing but a rotating uncontrolled full wave rectifier or inverter. Sir, which is correct, sir? It will convert AC EMF into DC in the generator. Nothing but it is a rectifier. It will convert DC supply to the AC in the motor. We are giving DC supply, but when it reaches to armature, it is AC, so it is a inverter, which converts AC to DC and DC to AC. Sometimes they may ask you question, the DC machine, in DC machine commutator will do what? DC machine nothing but both motor and generator, both. So AC to DC and DC to AC. For example, DC generator, in generator nothing but AC to DC. Motor, DC to AC. Yeah, very good. Sir, what it converts, current or voltage? In generally, we have to tell that AC voltage into DC voltage and DC voltage into AC voltage. This is 100% correct answer. Of course, if voltage converts, current also ultimately converts, but we are talking in terms of voltage. Right? This is simply about the commutator. So generally, the commutator converts AC to DC and DC to AC. Nothing but rectifier in generator and inverter in motor. Simply converter in DC machine. And number of armature coils equals to number of commutator segments. If more commutator segments we are using, more commutator segments gives us pure DC output. This is also, I said you already. This is simply about the commutator segments. Always commutators should have what is that? Highly resistive nature, like this hard drawn copper alloy. So this is simply about commutators and brushes. This is construction of DC machine. Up to now clear? Is it okay? Just interpoles and compensating winding I will explain you in armature reaction. Right? Thank you.